Hello and welcome. My name is Jonathan Lawley. I'm a student here at RIT. I'm currently working with Dr. Stephen Day in his lab, and today I'm going to be demonstrating to you our current design for a centrifugal blood pump with magnetic bearing. As a quick aside, most of the work you've seen implemented here today has been done by Andrew Roof, who is currently a co-op in our lab. Now, this pump is what is known as a ventricle assist device, or VAD. VADs are mechanical devices usually implanted to support the pumping function of the ventricles. Most pumps available today are left ventricle assist devices, but we are working on a device that can support both the left and right ventricles. We are accomplishing this by placing an axial pump inside a centrifugal pump, where the centrifugal pump supports the left side and the axial pump supports the right side. But the focus of today's demonstration is the centrifugal pump. The way this pump creates flow is the same as any other centrifugal pump. The novel aspect of it, and the reason it's good for pumping blood, is that it is essentially a brushless DC motor. This is important because with a brushless motor, there is no physical contact between the rotor and the stator. The way brushless DC motors work is that the stator creates a rotating magnetic field by precisely switching the electromagnets you can see in the figure. Then the permanent magnets in the rotor follow this rotating field. The way we implemented this in the pump is by placing the permanent magnets inside the impeller and surrounding the housing with these electromagnets. Here we have a three-phase motor controller, which generates a signal from this microcontroller. The signal is then sent to these three separate gate drivers. The gate drivers essentially boost the signal from this microcontroller to fully drive these three pairs of MOSFETs, which correspond to the three phases of the motor. We have the waveform of the signal for just one of the phases. This same signal is just shifted in time for the other two phases. Then the ultimate goal here is to switch on and off these electromagnet stators. Now, outside of the electronics, we have the pump itself, composed of the housing, the bottom and the top, as well as the rotor. The rotor is then lined with a series of permanent ring magnets. Here we see a slow motion video of the rotor spinning inside the housing. It can currently spin at about 1700 RPMs with a pressure differential of 70 millimeters of mercury at 5 liters per minute. At 0 liters per minute, it can generate about 100 millimeters of mercury of pressure. In free flowing, it is able to flow at around 10 liters per minute. According to ASTM, the physiological goal for the pump is to have it run at 5 liters per minute and generate 100 millimeters of mercury for use in a left ventricle assist device, which is what we are intending this centrifugal pump to be used for. That means we are relatively close to our goal, but just need to increase the speed at which the rotor is spinning rather than changing any sort of geometry of the pump itself. Once we achieve this pump performance goal, we'll be able to move to the next step, which is using actual blood and seeing if the pump causes any significant amount of hemolysis or thrombosis of the blood. This has been Jonathan Lawley here demonstrating a centrifugal blood pump with magnetic bearing. Thank you for watching.